My name is Stephan. Nice to see you all. I'm the founder, one of the founders of Slackline, and I posted some article about aluminum and steel some months ago. This article spread lots of. We missed a lot of steps for equality, for equity, and I think we might want to learn from the climate community, which had the same situation about 30 years ago. They have been a nearly pure male community, and they managed during the last 30 years to build up a community that is equal and has lots of girls and women in it to enjoy the sports as well as we do. So I think we should learn from them and maybe try to change our community. Okay, that was these 2 slides. So I want to start on steel versus aluminum in slacklining. In my article, I had some aspects on environmental stuff. You all know if steel is produced, this consumes lots of energy and is terrible. This is as well suitable for aluminum. So always when we produce gear from any metal, this is environmentally a disaster. But we can compare these, and if we put equal points on both these materials, we can see that steel has better ecological balance than aluminum. But this is not what I want to talk about today. I want to talk about physical aspects and especially fatigue aspects. So steel has the name of being some very heavy, and aluminum has the name of being lighter and being more shiny, being more sexy as material. So I put a comparison on weight versus strength ratio, and I compared 70-75 aluminum, which is called the classical airplane aluminum, compared it to 1.4301 steel. This is what we know as a classic stainless steel. And if you compare these strength to weight ratios, you see that this steel is a lot of heavier and a lot of weaker than any aluminum constructions we know right now. But there are steels out there, for example high strength steels, which have the same weight to strength ratio as aluminum has. And we can build constructions with these steels that are as lightweight and as strong as aluminum constructions. I will get to this in a little more detail in the following slides. Why do I suppose to use steel instead of aluminum? If we have steel plates and pull at them, we see that they have lots of deformation before they break. These photos are from EQB slacklines, so big up for publishing them on the net for them. We see here the pulling test results, and we see that the plates have lots of deformation before getting weaker and breaking. This is called ductile deformation or ductile breaking. We can see this on the left. Ductile breaking means the material gets a lot of smaller before it breaks, and it has lots of deformation. The opposite side is brittle failure. Brittle failure means you pull at some material and you don't see any change at the whole curve of tension, and the material suddenly fails with a big boom. This is what mostly happens at aluminum. I want to show you a video of how it looks like when we break one of our metals. This is how it looks like when we break one of our web hooks. The strength of it was about 100 kilonewton, and these are the results. You see that there is nearly no deformation at the side plates, and you see that the shackles it was connected to show lots of deformation. These shackles were 40 millimeters high strength steel shackles, and even them, though to the high deformation, they didn't break at all. But you see they are not usable anymore. The opposite to this is failure of aluminium. If you pull this, it suddenly fails. It has this brittle failure. And on the lower right, I showed some, what's it called in English? Quick triangle delta, yes. Which occurred the same situation, but didn't fail, but shows lots of deformation. So why do I suppose to use aluminium instead of steel? Not only because of this brittle versus ductile stress characteristics, but steel has lots of advantage over aluminium when it comes to fatigue. Steel has a fatigue limit of about 40 to 60% of its strength at between 10 power to 4 to 10 power of 5 cycles. Aluminium is weakened if you take all the cyclic load until it breaks. Fatigue is the main source of failure of all engineering devices out there. If it's a bridge, if it's a car, it's any part of a car, it's any sporting gear, whatever we see, fatigue is the main cause of these parts to fail. There's something called high cycle fatigue, which starts at about 100,000 cycles. This means that if we use steel at about 100,000 cycles, we don't have any more weakening, but in aluminium we see further weakening of the material until it breaks. There's another thing we need to know about these materials. It's called creep. So even if we don't have cyclic loads in slacklines, also static loads can weaken material until it becomes, until it breaks. Steel is known to be more resilient to creep than aluminium is. So how does this look in slacklining? The guys at slack.fr made some tests, I guess 2 years ago. Big up for them for publishing these results. I guess this is a huge move for the community. What we see here is one of their weblogs. They tested it up to, I guess, 18 kilonewton, and it broke after, I guess, 8,000 cycles. And they tested one of their pulley systems, and they tested one of their prototypes of a steel weblog. All of them broke under cyclic loads. Does this mean that steel is not suitable as well as aluminium? I don't think so. If we look a little closer at this steel weblog, we see that inside this construction there are holes, and the weblog broke near these holes. I will get to this point a little closer at some slides in the future. How does fatigue look in real slack life? I often hear, yeah, this is not a real issue for us. In real slacklining, gear doesn't really break. I think this is not really true. We see there's lots of gear that failed during the last years. It's mostly failed in trick lining, but I don't believe this is a reason to not think about this any further, and I will show you why in the next slides. I want to show a little comparison to cycling. I've been a mountain biker for many years, road races, and yes, there are 3 types of cycling in the mountains. One of them is downhill riding. Downhill riding is well known for crashing lots of the gear quite after very short periods of use. I think we can compare this kind of cycling to trick lining. It has very high cyclic loads, and lots of gear breaks after short times. But we also see in cycling breaking gear that does not see these heavy loads. We see crank arms breaking from classic cross-country mountain bikes, and we see crank arms breaking. You see the crank arm on the lower right. This is a crank of a road racing bike. Even these crank arms made from aluminium break after enough cycles. So what can we learn from this? none of these constructions is fail-proof over time, over cyclic loads, even if the loads are way lower than they were designed to. One of the comments I received on Slack chat is that maybe I am a downhill rider and I just crap my gear and just crash it all the time. I am not. I'm a cross-country and street rider, and even I managed to break several handlebars and seat posts. And the same discussion we have now in the room about aluminium and cyclic loads, I have seen them during my time as a mountain bike racer. There have been people out there who stated, yeah, but there are very well and very fine crafted aluminium cranks and aluminium seat posts, etc. These are engineered at that high quality, they cannot break. One of these pieces, what everybody thought cannot break, were crank arms made by the Japanese company Shimano. They are assumed to be that well crafted that they cannot break even if they see high loads. What you see in these pictures is two crank arms from the brand Shimano having broken, not during downhill, but during road cycling and cross-country cycling. So what can we learn from this? Even if experts in the field say, this will never happen, they are that well engineered and that well crafted, they will break if they are made from aluminium, if they see lots of cycles during time. I see the same order of failures in slacklining. If I look at this, I think we can compare downhill riding to tricklining. We can compare cross-country to maybe long lines which see higher tensions, and we can see road racing compared to highlining which sees lower tensions. But I think the impossible is not impossible. Why does this happen? One of the words that was around in my article and that was that spread lots of discussion in Slack chat was the word micro cracks. Many people told me, yeah, micro cracks have been debunked, that's just a myth, it's an urban myth, and this is not real, this does not happen. I can tell you this is not a myth, this is not debunked, this happens every day, this is real, and I'll show you why. We see here some guys having some ultrasonic devices. They are checking airplane components for micro cracks. Airplanes see many cyclic loads, as everyone can imagine. They have these turbines and propellers and stuff, and of course there appear micro cracks due to cyclic loads after very short periods. So in airspace and aircraft engineering, they use these ultrasonic devices to track these micro cracks, to find them, to visualize them, and to change these parts. They are doing this because this is real, this happens, even if these parts see no other damage, they just see cyclic loads. Then some people stated, yeah, but we see lots of tests. We see lots of tests by Black Diamond, we see tests of UIAA. They made tests with aluminium carabiners, and we didn't find any micro cracks in there. That's true. What they did is they took some carabiners, they took some kind of cloth, they knotted it in, and they threw it out of the building, and they threw it down some cracks, and they tested it afterwards in a one-time load until it cracked. Is this the same scenario we see in slacklining? I don't think so. We don't see one-time loads, we see cyclic loads, and we see lots of them. So we cannot really compare a test that only has a one-time load to a test that applies cyclic loads over 100,000, maybe 1 million cycles. What makes microcracks appear? There are lots of scientific studies out there that show very easily that cyclic loads are perfect starters for even at perfectly polished aluminium surfaces. You apply to them at about 50,000, maybe 100,000 cycles of load, even at very lower loads than the braking strength, and it can be shown easily that these parts have microcracks afterwards. They can appear maybe at about 20% of breaking strength. I show a study about this in the following slides. And a completely undamaged aluminium surface. In the study, the guy took some cylinder and he tested the cylinder at 20%, 30%, and 40% of the breaking strength. And he could show that in all his tests, the device he tested had not only micro cracks, but even cracks with a length at about 6 millimeters after his tests, at lower than 100,000 cycles. Why do I think this microcrack story is important for us? Microcracks can be started even better if the surface of metal is damaged. So what's important about the metal is the hardness of the surface, so we can prevent damages to maybe prevent fast starting of microcracks. We did some tests about it. It's called the Chapi or Chapi test. You take a weight with a quite sharp edge and you let it swing to a surface of a metal, and you see in the time after you see how the surface reacts. We tested aluminium, stainless steel, usual steel, and high strength steel. I show you the video about it, and I'll pass around the pieces we tested. Okay, so we tested all 4 kinds of materials. These are the results. We have this aluminium piece. It's this little piece over here. And I'll pass it around and you see a really deep and sharp notch in it. Pass it around so everyone can see it. Then we have this stainless steel, same result. We have some usual steel, some usual mild steel, and we have some high strength steel, which doesn't see any surface damage from this test. Why is this important? If we have damages in the surface of a metal, we have a crack. This crack is forcing the loads that are in the metal to go through a smaller part of the metal. If you have this piece of material and you have a tension in the new material, the load can flow through the whole material and it doesn't show any peak loads. But if you have a crack in it, the loads are forced to find it. The crack started not because the C-post was engineered badly, but the designers of the C-post decided to put some laser engravings at the top of the C-post, and even the laser engravings that are not even 1/10 of a millimeter deep are crack enough to start fatigue cracks that break this C-post under cyclic loads. So why do I try to stress this? We see gear out there that has these cracks built in by design. We see weblog prototypes that are shown on Facebook. We see shackles out there that are shown on Facebook and sold. And these grooves that we can see in there are very well known as perfect starters for fatigue cracks. You can see them, you can touch them, and what I want to stress out in this presentation is maybe we should think about the quality of the gear, the surface quality of the gear, and if this is the gear that's suitable for high cyclic loads. We can prevent this. There are producers out there that do it a lot better, maybe by just polishing the surface, so at least these starters for further cracks are not available in this material. And then there's another situation I want to point out. We have this metal on metal situations very often. You can see grooves in the upper left picture from one of my quick draw Venus that has been used on lots of hangers for sure. And you see, of course, there are a lot of cracks in them. And you see one of my rigging plates that I used a lot for rigging slacklines on steel beamers. Of course, it has deformations. And these deformations we can see on the left are perfect starters for further fatigue cracks until it breaks. And what I see on Slack chat and in other Facebook groups are advices that maybe we can use some aluminium shackles and combine them with steel gear. And what we see then is the same result as we see with other gear of aluminium put on steel. And we have the same cracks and the same starters for further fatigue cracks then. Is this just a scientific scenario? Is this just an urban myth? So I tried to find some studies about this, and I found this very useful graphics. This is the molecular painting of an aluminium surface. And we can see here if some stress and some cracks are applied to the left side of this surface. These two molecules on the left side, if they are damaged, are enough, and they are called stage 1 fatigue cracks. It's just about 1/100th or 1/1000th of a millimeter deep, and it's enough for starting further fatigue cracks. And what follows is so-called stage 2 and stage 3 fatigue. We have this crack initiation. The second stage is crack propagation. And the third stage, when it grows really fast, is crack propagation until failure. How does this look like if we look through the microscope? This is a microscopic figure of an aluminium surface with a very small crack inside. This crack is not visible with the human eye, but it's visible on a microscope. So in this study, they tested if these cracks are enough to start further fatigue cracks until material breaks. And they found that even cracks that are 0.006 millimeters deep are big enough to start larger fatigue cracks that make the material fail. This study is known since 1975 and is undoubted since. How does this look like in real life? If we see aluminium gear breaking, we can watch the breaking points afterwards. What we see in this picture is we have some dark places, that's the ones up here. We have some brighter places, that's the ones here. And we have this really bright place over here. This is the place where the initial crack started, and this crack has been present in this crank arm for many months or even years. Why do we know this? We have lots of corrosion inside this crack, and this corrosion made this aluminium appear black. This doesn't happen within days, this doesn't happen within weeks, this happens within months or years. Was this cyclist an idiot? Why didn't he change his crank arms? These cracks are not visible to the human eye. He rode and rode and rode until his crank arms failed. There is another option to start failure in metals, that is corrosion. We all know that corrosion is extremely bad, especially for steel metals. So it's very important to prevent corrosion on steel. And there is this so-called stress crack corrosion. This is the big downside of using steel in cyclic loads. We know this from hangars, we know this from boats. All over the places, if we connect some cyclic loads from a slackline to a boat in a maybe saltwater environment, we see them break after months or even shorter times if it's really heavy. Aluminium is way more resistant to the so-called stress crack corrosion because the surface of aluminium has some kind of self-healing properties that are especially available after so-called hard anodizing. This is what we see in shiny, colorful surfaces of aluminium gear. So this is not really an issue for aluminum gear at all. So in conclusion, what makes micro cracks appear? Tiny corrosion cracks are very good starters, and they are proved scientifically many, many times. Aluminium can be sacrificial anode if it's combined to steel components. Aluminium is a less edel in German material than iron is. So if it's combined and it's under wet conditions, it can corrode really quickly. And it's shown in many scientific studies that the corrosion damage of the material, the larger the corrosion damage is, that the faster it makes these cracks grow. So what I hear a lot during the last month is, but we have safety factors. This cannot happen because we have so high safety factors that we are mostly safe. On the lower end of this slide, you see some charts. This is a scientific study made in Pakistan in 2016. 2010. No, 16, yes. This guy took this cylinder I told about you before, and he put it under cyclic loads and wanted to see what happens. The surface of this cylinder has been perfectly polished, and he put it under cyclic loads at 40% of breaking strength, 30% of breaking strength, and 20% of breaking strength. And what he could find is that at 40% of breaking strength, this cylinder failed at way below 10,000 cycles. At 30% of breaking strength, he found that it broke at about 10,000 cycles. And he found that at 20% of breaking strength, that this cylinder failed at way less than 100,000 cycles. Does this apply to real life? I showed you the pictures of Slack.fr before, where they showed their broken gear that they tested in the lab. And I took these numbers and I compared them to the gear that Slack.fr showed in the lab results, and they fit nearly perfectly. So what can be said is safety factors may prolong the time until the gear fails, but they do not prevent failure completely. So it's just a question of time that this happens. Then I hear a lot of times, but our gear does not fail. We see now that gear fails, even though it's just in trick lining at the moment. And one of the most heard points nowadays is, but we are saggy now. Yeah, Charles, that's been you. Yeah. I don't think that this is really true. I follow about 3,500 slackliners on Facebook right now, and every day I see pictures posted by them which are not saggy at all, and I see tens of them every single day. We have lines that are about 11, 12 kilonewtons from slackliners all around the world who spend lots of money on their gear, and they post these pictures every single day. You have on the right, you have a picture from Germany. It's a line of 155 meters of length, and it was attached to trees in about 4 meters of height at a plain ground. So if you take the calculator, you will see that you will have this line at about 9 kilonewton base tension. On the lower end, you have another line made in tension in Japan, I guess. It's made from moonwalk webbing, and the length is about 101 meter, and the sag is about 2 meters. If you calculate this, you are at about 10.5 or even 11 kilonewton of base tension. But we are saggy now, and we don't see this cyclic loads. This is what happens lots of times. skiers every day out there. We are maybe saggy, but we see nevertheless lots of cyclic loads. Does this mean that we don't see loads that may fail gear? I don't think so. I strongly believe that aluminium gear will fail after time, and that will happen in the near future. And then some people tell me, but you use aluminium too. Yes, we use aluminium, sure, but we don't use it in parts that are cyclic loaded. We only use it if they are carried by steel structures that are not don't carry the load. What I also hear quite often is, but I really take care about my gear. I never connect it to any steel things. I never connect it to anything else. What could produce scratches in it, and I really handle it very carefully. About 4 weeks ago, we had a return shipment from a guy in France. He shipped back the pulley system. He threw it down about 30 meters, the crack, and wanted it to have repaired. So there are definitely guys out there who throw down their gear cracks, and maybe if it's not damaged that heavy, they use it and use it and use it until it fails. And there's another thing I want to stress out. We have aluminium leash rings. Leash rings might be the gear that we all could expect to have the least notches and scratches at all, because they don't see any contacts to anything else. But as we see, my leash rings have lots of scratches and lots of starters for fatigue cracks, and even the scratches that were shown by Thomas and Mark have lots of scratches inside. So even gear that is not used to have contact to any other metals and to have scratches produced in, see these scratches. So I don't think that aluminium gear does not see scratches after time. And I can prove this. The best place to see aluminium gear after lots of time is Slackchat used gear. And you only have to scroll through it and see how used gear looks like after several months or years. What you see here are some pulley systems that are not in new condition. They are very hard worn out. And yeah, even if these guys paid lots of attention to their gear, this looks really worn, has lots of scratches, and these scratches are perfect starters for further fatigue and fatigue cracks and maybe failure someday. But then another point was, but high-strength steel has brittle too. Yes, high-strength steel can fail too, but this mostly occurs in very large constructions like bridges, like tanks, and it mostly occurs at very low temperatures. If you take high-strength steel to temperatures of below minus 20 degrees, it will fail. So maybe we have to be aware too that if we use high-strength steel, it's not the perfect gear for using it at Antarctica. Another point that was stressed out lots of times was, but climbing gear is aluminium too. Why do we use climbing gear made from aluminium, but should not use slackline gear made from aluminium? It's a simple statistical thing. My personal quick draw set contains 15 quick draws. When I go sport climbing, I take maybe about 20, maybe about 30, maybe about 50 whippers a day. And maybe I am outdoors at about 40 days per year. Now we can do the math for the cycles. These quick draws see about 2,000, maybe about 4,000, maybe about 5,000 or even 10,000 load cycles in 10 years. This is way below anything that would crack them or make them fail in usual climber's life. So that's a huge difference between slacklining gear and climbing gear, in my opinion. And should we throw away all our aluminium gear now? And should we throw away all our aluminium bikes and other aluminium sports gear? What we see here is a bicycle on the left. This bicycle has welded on some so-called gussets. These gussets are known to strengthen aluminium because they are welded to the places where these fatigue cracks would grow usually. So we have a gusset in this place, we have a gusset in this place, and we have a gusset in this place. And these parts strengthen the aluminium in these places, so it doesn't fail that fast. But as we all have seen on the pictures before, even these downhill bikes with lots of gussets fail after some time. And even the best manufactured crank arms that are dedicated to not fail by experts' advices fail after time. And there's another thing I want to stress out here. The cost of a broken bike crank is quite low. Maybe I fall to the street, maybe I break an arm, maybe I break a leg. But a broken highline rig might cost a little more, especially if you heard about, yeah, maybe we have some non-really existent backups, or maybe we even think about not backing up at all in the future. So the key lessons that I want to transport today is aluminium failure under cyclic stress occurs independent from engineering quality. It is not about safety factors, it is not about highly polished, high quality engineered parts. They might fail under cyclic loads. Even the best, even the most fail-safe constructions might fail under cyclic loads. So, what do I... Go for it.
I said, so does steel, doesn't it?
Steel does.
Yeah.
But it shows a lot of signs before it fails, and it fails a lot of later. That's a huge difference. In my opinion.
Maybe finish.
Okay. In my opinion, carabiners and shackles. Carabiners and shackles are not really suitable for cyclic loads and slacklining. So are weblogs, because they all see cyclic loadings in direct, in the direct load direction. And as we have seen with bike cranks and other bike parts, it's just a question of time that they might fail. Pulley systems might be less prone to this failure because we can take them out due to soft pointing. Leash rings are not a problem at all, they don't see that cyclic loads, so do lineups. So if there are questions out there, I guess there are a lot. If you want to discuss this, let's go for it.
So I have just two questions. The first question is, so you're saying my aluminum bike will fail when I go and keep on riding it. So after some time, every aluminum part will fail.
Yeah, most of them.
Yeah, most of them or all?
Not all, not all. It's a huge difference. You have aluminum gear that's known out there, that's riding out there for 25 years. But I believe we cannot rely on this statistical thing if we are practicing a sport where a failure is deadly. A failure in a bike costs me a broken arm or a broken leg. Maybe I have some damage to my face, but I won't fucking die about it.
So my second question is,
yes.
We're talking all the time about cycling loads, but can you define what you mean with cycling loads and slacklining? Because there are huge differences about cycling loads. There's high cycling loads and low cycling loads. What do you especially mean with cycling loads in slacklining?
I would like to also tack on to that. Where do you find the cyclic loads in slacklining? Is it wind or is it jumping?
For sure, it's mostly trick lines. We all know this. Samuel had some great videos about the loads and the trick lines. These loads also appear in long lines. These loads also appear in high lines. They do not appear at the same frequency. They do not appear at the same peak level of force, but they appear. And as was like it was shown before in the slides before, even creep weakens the material, and if you add cyclic loads to them, and we have seen some trick lining on long lines, trick lining on water lines, trick lining on high lines. All these things are cyclic loads. And I don't think that this is that these low peaks are too low. They are just lower than in trick lining. So we have a higher safety ratio, which only prolongs the life of the gear, but does not mean it will not fail after time.
Sire Chalkowski on the Balance Community Slack Science article from 4 or 5 years ago made a long line cyclic testing of how many cycles you can get, and in 1 hour you could get potentially up to 50,000 cycles on a long line from wind. He found that without wind dampers, that the proportion could be on a fairly tight line, maybe 8 kilonewtons. The proportion could be around, I'd say, 10% of the load of that total load. But with wind dampers would be about 1%. It looks like what he found. So how does the amplitude of a cycle affect the potential for a crack?
As we've seen, if you have lower loads, this one. As you see, the higher the load cycles are to the braking strength, the faster the brake might occur. The lower the load cycles, the peak loads are, the later a brake will occur. But as we see here, even high safety ratios do not prevent failure at all.
Just that, the high safety factor that you have there is 5 to 1, right?
Yes. Yes.
But I think most of the people are using much higher safety factors in Slacklining, don't they?
Yep.
With the leash rings, for example, they break at least 4, 5, 6 tons. What load does a leash ring see?
And I don't even think that a leash ring is connected to this topic at all. A leash ring does not see cyclic loads.
Okay. I just saw it in the presentation, I don't know.
Yeah, maybe I understood the question in the wrong way, I don't know.
No, you just had the leash rings in the presentation, didn't you? And said
Yes, what I wanted to stress out about the leash rings is that even leash rings that are not known to have connections to any other metal, to any other hard piece of gear.
That's not true. They have connections. They hit the high
The
web
web
locker all the time,
sure.
the web locker all the time.
Yeah.
Sure.
You put it in your gear bag. That's where the dents come from.
That's what I wanted to stress out. Even the gear that is not known to have much contact to harder gear, to other stone, etc., sees connection to metal, sees connection to stone, and has damages in the surface. That's what I wanted to stress out at this point.
It's not a cyclic loading issue.
Yes.
Okay, but that's low cyclic loading, right? So the leash ring is overdimensioned for this issue.
Yes.
And it's safe.
And it does not see cyclic load, so I don't see any issue.
It does see cyclic loads. It does see cyclic loads.
Yeah.
The leash load is a cycle.
But no,
the number of
Does your leash ring see 10,000 or 100,000 cycles?
It's like thinking, what is a cycle? If you have a slack line in the wind, 100 meters, and it's going up and down, how high is the difference of the load? Is it really a cycle, like the load changes if it's loaded with...
Everybody please quiet down.
If it's loaded with 5 kilonewtons, let's say, it's going up and down, and the load changes like 50 kilograms, is that already a cycle, or is it not a cycle?
It can be called a cycle, but I don't think it's a cycle that weakens the material.
You know, that was the reason why I asked, can you define it a little bit more? Because I think you are talking about cycles like bouncing or surfing, where the load change in the line itself is not that big anymore. So is it already a cycle or not? And if it's not a cycle, like the leash fall is not a cycle, or
the leash fall is a cycle for the web locks, for the shackles, etc. Sure, but I don't think it's a cycle for a leash ring, because the leash ring has another orientation at any leash fall at all. So you have different rotations of it, so you don't have the same cycle in the same direction every time again and again.
Something to point out here from a study at MIT for the analysis of fatigue failure in D-shaped carabiners by one of them is the in the I was going to talk about it really quickly about that. They found a load difference of 0.5 to 4 kilonewtons, the mean cycle to failure on an open gate carabiner was 7,800. With a closed gate carabiner from 0.5 to 8, it was about 11,000 cycles. So in theory, the cycles, even on low numbers, if it reaches a high enough force on the carabiner at least, then it can have relatively low numbers. 11,000 is relatively low.
But as we all know, none of my climbing beginners and none of your climbing beginners sees 10,000s of cycles. It's totally unrealistic.
I did ice axis.
You what?
I did break an ice axis in fatigue.
An ice axe?
Yes, inside.
You broke it?
Yes. So it can occur.
Yeah.
Did you? I'm not sure. I think I missed it before. When we were talking about the amplitude of the cycle, like how, if it's like let's say it's a short bounce versus a big bounce, did that affect the
frequency of the bounce, the frequency of the cyclic loads does not affect the number of cycles the material can see.
Okay.
So if you see the test machines that are out there that do these cyclic load tests, they can test at 10 hertz, so you see 10 loads at a second, and some of these machines test at 1 hertz. So they all come to the same results for the same gear, even if you test at 10 hertz or 1 hertz. It doesn't matter. Amen.
I have a question.
Yeah.
This graph that we see there, the highest point there, it's 1/5 of the brake strength, right? The loading. And then, if I remember it right, it was 100,000 cycles?
A little below, yes.
A little below. So, if we see how this graph is going, if we would assume we take a well-designed piece of gear and say we can take a safety factor of 10, do you think it would be cool to use it for slacklining then, if it's not for trick lining?
It would be safe, as I assume in my last slide, for maybe a limited time period. That's the point I want to suggest in this talk. Let us talk about time spans for aluminium gear, because we know it will save. The scientific facts show that it will save after a special number of cyclic loads. So maybe we have to think about what time period might be the best choice for us to not fall down the crack due to aluminium failure. Okay, last question.
I have many things to tell about it, but I will just tell the essential thing. So when we talk about cyclic loading, the peaks to consider are not the highest solicitation, the highest strength. For example, if your web load working load limit is 1 ton, and you say the guy is working on it and the highest tension is 1 ton, the load to consider is the variation between low tension and high tension. So it is much more smaller than the tension, the real tension. So that increases a lot the safety factor of the use. You know all the diagrams, the SMP also. It's about the variation, the amplitude in loading.
As far as I know, I can open it up here. This
This
test
is about amplitude. If you go from 5 kilonewton to 10 kilonewton, you will get almost the same result than from 10 kilonewton to 15 kilonewton.
No.
And if you go from, it's depending, it's not linear at all, but I mean it's, if I go from 5 to 10, I will not get the same result at all than from 0 to 10.
As far as I know, you do.
So, that means the tension to consider on this diagram is not the tension of the line. It's just the amplitude.
As far as I know, the factor that influences the lifetime of a piece of gear the most is not the base tension of the cyclic load test, but the peak tension. So if you go from 0 to 10 kilonewton, you might see the same results of cyclic loads that it can carry as if you go from 5 to 10 kilonewtons.
I'm sure not. You know, I did work on it as an engineer. In my previous job, I was working on cyclic loading, so I can assure you this is not working like that.
Okay, maybe that's wrong information from
I just wanted to make a compromise because this is really, when we saw your presentation, if I don't know anything, I think, oh, it's very dangerous. But really, there are some things to consider. You're not, most of the things you said are true, but many things are just common facts, but not really appropriated to the situation. I also wanted to say about something about the bike, your example on bicycle.
Yeah.
You talked about the cranks, and you said something like downhill is looking like straight line, and cross country is looking like long line. But I'm also a bicyclist, and I do practice a lot of cross country and all mountain. The cranks are too much suffering in cross country than in downhill, because I'm cranking every month. I don't take the lift to go up the hill. So, you know, the crank and the solicitation are much more dangerous on the crank. Those are combined stress due to torsion and bending.
Sure.
So the solicitation is very difficult to consider and very worst instead of the solicitation in the weather, for example, which is only some pulling solicitation.
Sure. But crank arms
I do
are also designed for these loads, as well as web loads.
I would consider the opposite things of you. I will consider that cross-country or maybe road cycling is compared to straight line, and in the opposite direction, downhill, when we do not crank at all, when we have some good damping system, good suspension, can be considered like long line. This is my point of view. For the cranks, only for the cranks. And I think you show some cranks, you show some frames. Solicitation in the frame are really different.
Okay, what's the last question?
Okay, thank you very much, Stephan.